we jump to the next, which more specifically makes us use this error thinking to think about how large studies should we perform, should we make, to be sure that we know the errors we make for relevant settings, right? It's important. It's also a bit challenging for many of us. So now I put myself in the planning position, right? I'm going to plan an experiment, plan a study. I haven't done it yet. I'm going to think. And if I come out as the manager of some group out there, I may have, the budget responsibility for the different studies that I'm going to do to investigate things. So I'm going to do a budget. The size of N is the same as money, right? The sample size N, how large a study should I make to investigate my stuff? N is the budget, basically. There's some basic expenses, and then there is a proportional expense related to the N when I do a study. No matter whether it's Novo or a car or a PC screens or whatever we do, that's how it works. Power. What is the power? That's actually 1 minus beta. It's the probability of finding something which is there, right? So it's the positive version of the type 2 risk, or it's 1 minus the type 2 risk. The type 2 risk was the beta, was the probability, the risk that we didn't find something which we should find. Now I put it the opposite way. I say, what is my chance of finding it when it's there to be found? So it's a scenario-based thinking. If there's something there to find, what is my chance to find it? That's the only thing we can do. We cannot, if I knew everything, then I didn't have to do the experiment. But I can say, what if? What if? That is challenging, because the what-if scenarios about the potential alternatives is a pretty large set of possible values. It's an infinite set, right? We have to try to be specific. You don't get all the math proofs and all for this setting, but I give you the tools and try to make you think about what it means. You can find some extra math video to get a little bit more if you like, but you don't need it to actually start using it. Here is a really, really neat thing for you. There are 5 things in play when we do hypothesis testing. If you know 4 of them, you can find the 5th. That's the math. They are interrelated in a way such that if you know 4 of them, you can find the 5th. Well, some of those are usually sort of fixed, and so we play around with some of them. It's the sample size, it's the power, it's the standard deviation. This is where we have to bit scenario-based because we really don't know that, but we could play around with scenarios. The effect size. What if the what is 85? That means a difference of 2 to the hypothesis of 83. What if it is 2 away? Will I find it then, having 12 screens? What's the chance of being able to find? And then, of course, the significance level. You can spend a few hours thinking about these two. I have 2 plots, a low power and a high power example. Low power, high power, low power, high power. Let's look at the high power case. I really recommend you to read the sections in the e-note about this, because this is something where you, at least personally, I find this a bit challenging actually to get this under your fingers. So you need to read it and think about it. If the alternative is pretty far away from the null, then it is pretty, so the real distribution is here, then it is pretty likely to go above the critical value of the null distribution. The critical value is coming from the null distribution. And the hypothesis test is designed so that this is the one-sided right hypothesis test that is exemplified here. A hypothesis test rejects if I observe something above the critical value. What is the probability to observe something above the critical value? If the real mean lies above, it can become pretty large. So if there is a real mean out there to detect, in this case, I would, with a high probability, be able to claim it different. In this case, it's an impossible situation. If the mean is only slightly higher than the null, the real mean, then I have exemplified here, less than 50% chance to actually detect the mu0 being different from the mu1 being different from mu0. It's quite unlikely here. 40% is useless power. Power must be 80-90%. Here it comes. How to do it practically. And that is the big question, and people come and ask a statistician this question again and again and again and again and again. They come to me before they do the experiment. They look at what they have in their finances, and they ask me, how large should n be? They don't show me the finances. They say, what should n be? And they expect me to give them the answer. 7, they hope. 9 maybe, depending on where we are. 1,000 at other places maybe. It's just not that easy because I have to pose some questions against them. Remember, I need to find the n, I need 4 inputs to give the 5th output the n. So I need the people to think about the 4 inputs. And that's not just for the statistician to think, because actually it's not even for him to think. But of course it's for the statistician to make you guys realize what you have to think about to make those 4 inputs to give me an n that we can use for a real life purpose. First of all, power should be at least 80%. Here is a formula that comes from these 2 plots I showed you actually. You could deduce this formula from these plots. This is an approximate formula which tells you what should n be. If I know all the 4 inputs, I should speculate on the sigma. I should speculate on the potential effect that I would like to detect. I should decide on the power, and I should decide on the type 1 level, the significance level. If I made those 4 decisions, I can compute n based on this formula. Right? Or we can use some nice functions in R that are even slightly better, because they're not even, you saw some normal profile as quantiles in there. They were there to approximate the right t quantiles. There is actually a function in R that can do this for us. It's a very nice function that knows all of these 5 inputs, and if you just give it 4 of them, it will give you the 5th, or sometimes it will even make some default choices for us. It's called power t-test. Here's one way of using it. Here, I would like to know, what is my power? That is, what is my probability of detecting a mean difference of 4? That is 87 in my screen experiment, right? If it was 87, because I know that the null is 83, right? Would I find it using n 40 screens, making an assumption which now number-wise fits my height example and not my PC screen example, using some scenario guess for the standard deviation, in this case 12, telling the function that I'm doing a 1-sample t-test. This is all we learned today. Next week you'll hear about a 2-sample t-test. Today we do a 1-sample t-test. And we have to tell also whether it's a 1 or 2-sided case that we're working with. Having told R these things, it gives us, here are the 5 things actually, and then this is just a sort of information that it's a 1-sided thing that it is basing it on. And the power came here actually. And look at the significance level was chosen at 5%. I didn't give it that. I could have chosen that differently. So it chooses by default 5% if we don't tell it anything else. So we're down at 3 inputs. The n the delta, and the sigma. 3 inputs. Having decided the situation, it tells me power is 65%. The power of 65% is not good. It's not good enough. It's almost not better than 50-50 chance. Would you spend $1 million doing an experiment with a 50-50 chance of finding what you'd like to find? I'm sure Mads Korsgaard would not. And he doesn't do that very often. That's why they're so successful. He is the research director of Novo Nordisk. Actually educated at a former nice institution of the Royal Veterinary and Agricultural University that doesn't exist anymore. Very nice place, used to be there. Here's another example. Sample size. That's the interesting thing. How large a sample size should I have? That's really the end of the day question. Here's the way to find it. I say, I want a power of 80%. Never choose something less than 80% here. 80-90% are the working numbers to be used here. What if I want to prove this 4 effect? What if the standard deviation is 12? What should my sample size be? It should be 59. Right? So 59 provides me the wanted power for this scenario-based effect. It's just one scenario-based effect. You have to think about that. So I have to go back to you and say, think about what you would like to detect, and I can tell you how expensive it is. The formula can. Now you don't have to ask me, you can do it yourself. Right? This is nice. That's the power and sample size.